Hello class, we are now doing section 3.7, which are about rational functions, and we're going to learn about what those functions look like, and also we're going to be talking about a different way to write using arrow notation. So that might be new for everyone, so we're going to take our time with that. Okay, the first thing is, let's talk about what is a rational function. By definition, a function is a rational function if it has a polynomial on top and a polynomial on bottom. Okay, so basically just look for, does it have a polynomial on top and bottom? If it does, then that's a rational function. So are these rational functions? This one, the first one, for sure is, because it have a polynomial divided by a polynomial. So yes, that is a rational function. What about this one? Do I have a polynomial divided by a polynomial? Yes, I do, and that's because even though 3 you might not think of as a polynomial, it still is a polynomial. So that is good. It's a polynomial just with a constant term. So that is one. And then let's take a look at this one. Think about it. Does that look like a polynomial? And well, if you answered no, then you're correct. And it's not because of this thing. Remember, 2 to the x is not a polynomial. Let's call it a polynomial. Try to squeeze it in there. So it's not a polynomial, so this thing is not a rational function. But the other two are. Okay, so now that we know about what makes up a rational function, I want to give you just a broad overview. All rational functions typically have what we call a vertical asymptote, and that happens when we could divide by 0. So if we take a look at this graph right here, 1 over x, that's a rational function, f of x, I'll write big right here. So f of x equals 1 over x, that's a rational function, and that's going to have a blow-up spot, because see how I have trouble right here, could divide by 0. So when x is 0, when x equals 0, I'll be dividing by 0 in this function. And remember, that's a big no-no, okay? No. That's undefined. So whenever you get close to dividing by 0, that leads to something that's not defined. And so what happens is that when you get close to dividing by 0, you actually start shooting up bigger and bigger and bigger. Let's take a look at the graph of this function. So this is f of x equals 1 over x. And you can see what happens. As I get closer and closer, let's say from the right side, let me do a different color here. As I get closer and closer and closer from the right side, the graph actually shoots up. It shoots up to positive infinity. Now, why does it do that? Well, if you take a number, let's say, coming from the right, and you take a number like, so I want to get close to 0. So maybe like 0.1. If I do that, then what happens to the graph? It's 1 divided by 0.1, which is 10. So at 0.1, it's going to be really high up at 10. And then what if I pick a number that's even smaller, like 0.01? What's that going to be? Well, divided by 0.01, that equals 100. And so hopefully you see the pattern. As you get really, really close to 0 from the right side, this graph shoots up really, really, really big. And that's coming from the right. What about from the left? Well, from the left it does the same thing, but as negative. So I want to approach 0 from the left, and so that would be like negative 0.1. That would be 1 divided by negative 0.1, which goes to negative 10. And all of these numbers are the same except they're negative. Which would be negative 100, and negative 0.001 would be 1 divided by negative 0.001, which is negative 1000. Okay, so that's why the graph from the left shoots down to negative infinity, and from the right it shoots up to positive infinity. So we call that a vertical asymptote, and so this has a vertical asymptote at x equals 0. Is a vertical asymptote. Crazy name, I know, I didn't come up with it. So we have to be able to write about it though, and what I just wrote with all these these tables here, okay, it takes a long time. So there's got to be a faster way to write out all this stuff in a much faster way, and there is, and the way we do that is what's called arrow notation. And so the arrow notation goes like this. We take a look at our function, and I'm just going to say, okay, what happens as x approaches 0? Let's start from the left side. And that's how we write it, okay? So the way I said it was as x approaches 0 from the left. So I'll write that in words for you over here. This is as x approaches 0 from the left. Okay, and so this negative sign, okay, does not mean a negative number. It just means approach 0 from the left. And that's the hardest part people have about this notation. Negative means from the left, and it's in like an exponent. It's not really an exponent, so it's really a bad notation, I think. I don't think it's that helpful, but it's just the way it is. I didn't come up with it. It's just the way math people write it. So anyways, this, if I read this out as a sentence, this says, as x approaches 0 from the left. Okay? And then what we care about is, okay, as x approaches 0 from the left, what does the graph do? And so I'll say, okay, what does f of x do? And again, if I look at the left side, I'm over here. And as I go close to 0 from the left, I'm putting my finger on the graph, and I just ask myself, okay, where's it heading? Is it heading to positive infinity, which is up here, or is it heading to negative infinity? And it looks like it's heading to negative infinity. And so we write that. So this is from the left side. As x approaches 0 from the left, the graph goes to negative infinity. And so that's how we write that. And let's do it from the right to get more practice. And trust me, this stuff really does give people really hard times. So I did try to ask several on the homework and lab to help you a little bit. But if you're definitely having trouble, you're not the first one, and don't feel bad. I can remember when I was studying this stuff in calculus, I didn't have pre-cal to prepare me. And this stuff, like, I did not like at all. But, you know, I learned it, and you can learn it too. So let's get practice from the right. So, okay, so from the right, you always talk about what does the x thing do first. So as x approaches 0 from the right, okay, and again, let's put my finger on my pen on the graph, and I'm here, and I need to approach this x equals 0 line. Okay, I need to approach that, and I need to come in from the right, and that's why I'm coming at it from the right side. Remember, this just means from the right. So I'm on the right side, I'm approaching 0, and then I ask myself, okay, what is the graph doing? It looks like it's shooting off to positive infinity. And so that tells me then, okay, the graph heads to infinity. Okay, and the reason it goes to infinity is because what I wrote down here. As you get close, as you pick numbers to the right of 0, very, very close to it, it shoots off to infinity. Okay, it never actually equals infinity, it just gets as big as you want, so we call that infinity. Okay, so we're going to get several more examples on this, but if you're having trouble with it, don't feel bad. Like I said, there's to me, I really don't like the notation, but it's just kind of what we have to deal with. Okay, you can fill this out in your from your book. Okay, so this is in your book. I don't want to spend so much time on writing out what every single one means. Okay, so just check your book for that. You might not even want to have to fill this out because we're going to do so many examples that you kind of will get an idea of what we're talking about anyways. So let's just take a look. So I think it might be better to take a look at it in practice. So let's take a look at this. So it looks like I have a vertical asymptote here. Okay, and that's at x equals 2. All right. So let's talk about, first of all, the local behavior, which would mean around the asymptote. So around the x equals 2 asymptote. Okay. Okay, so let's talk about the left behavior first. Around every asymptote, we'll have a left behavior and a right behavior. So let's take a look. I'll do it in blue here. Put my finger on the graph, and I want to approach as x approaches the asymptote 2. And again, I'm coming from the left. That's what left means. Okay, left means with a little negative symbol. As x approaches 2 from the left, where does the graph go? And I put my finger on the graph, I drew it. It looks like it's going down, 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 down. And that means it's heading towards negative infinity. And so I just write, okay, f of x is heading towards negative infinity. All right. So again, as the graph goes down, as I approach 2 from the left, I get really, really close to 2. On the left side, the graph is going down, down, down. And so this is going down to infinity. Down to negative infinity. And let's do the right behavior. So I take a look. I have, okay, so the right behavior, again, it says x is approaching 2 from the right. So as I approach 2 from the right, what does the graph do? Well, it looks like it's shooting up, and it can only shoot up to one direction. It has to shoot up to infinity. So we would write that as x approaches 2 from the right, f of x goes to infinity. Okay, and that's what happens with the local left and right behavior. Okay, so that boundary line, the x equals 2. Okay, those are called asymptotes. Okay, so the vertical one is a vertical asymptote, and it also has a horizontal one right here, which we'll also take a look at. And then anyways, those in general are called asymptotes, vertical or horizontal. Okay, so sorry I didn't have enough room on here, but I'm going to have to erase this to then talk about the end behavior. So please take some space out somewhere else to write out what the next part will be. Sorry, I wish I had more space here. So the next thing we're going to want to talk about is the end behavior, which is a little blast from the past from earlier in this chapter. So, actually chapter 1, I think. So let's go ahead and take a look. Let's look at the end behavior. Now the end behavior, remember, only referred to two things. It referred to what does the graph do as I go to all the way to the left and all the way to the right. So the left end behavior that means put your finger on the graph and actually just approach negative infinity. Like that. And so we write that as x, let me do a different color. As x goes to negative infinity, that's my arrow. As x goes to negative infinity, what does the graph do? And it looks like it's approaching this horizontal line, which is in green, which is y is equal to 4. So it looks like the graph is approaching 4. And that's how we write the end behavior there. Okay, it's not going to infinity, it's bounded by this line. So that boundary line we call the horizontal asymptote. And if we do the right end behavior, then this would say, okay, put your finger on the graph, and I'm going to, as x goes to infinity, so that's over here on this part of the graph. Where does f of x go? F of x goes to, sorry, not infinity. F of x goes also to 4. And so these are the end behaviors, not the local behavior. Okay, so just get comfortable with doing the different arrow notations and stuff like that. I'm gonna go ahead and I want you to kind of pause this video real quick. I want you to take a look at this next example, example 4. Okay, and I want you to find the horizontal and the vertical asymptotes here, and see if you can kind of identify, like I have been, about what an asymptote is. Horizontal means it's y equals. Vertical means it's x equals. Okay, so see if you can identify the asymptotes. And then when we come back, I also want to get more practice identifying the behaviors. So go ahead and pause the video and try it. Okay, class, we're back. So this is what I got for the horizontal asymptote, is y equals 3. It's this green line right here. Now, I want to stress, we write horizontal asymptotes as y equals. It's a horizontal line. And then vertical asymptote, it looks like it's this red line, this dashed line right here. And remember, it's a vertical line, so we write it as x equals. So it's x equals negative 2. I also did the end behavior, okay? So the, not the end behavior, sorry. I also did the arrow notation for the vertical asymptote. So for the vertical asymptote, as x approaches negative 2, okay, where does the graph go? It looks like, say, from the left. From the left, the graph goes down to negative infinity. So it's negative infinity. And let's take a look as x approaches negative 2 from the right side. Okay, where does the graph go? It approaches positive infinity. Okay, so that's that. If you're having trouble with that, please make sure that you ask me. We're close to the review, so if you have any questions, you can see me, or just shoot me a message on Canvas. Like I said, don't feel bad if this arrow notation is tough for you, because it's pretty tough for most people. Okay, we're going to move on to something different about domains. So, because a rational function has denominator, we're always going to set the denominator equal to 0 and define the domains, okay, the restrictions on the domains. So if we take a look at this graph here, where its domain, so its domain is going to be all real numbers except when the denominator is 0. So to find the restrictions, just set the bottom, x squared minus 9 equal to 0. Okay, and so that means we get x plus 3 times x minus 3 is equal to 0. That's a perfect difference of two squares. And so we get two answers, x plus 3 equals 0, or x minus 3 is equal to 0, which means we get x is equal to negative 3, or x is equal to 3. Okay, so that means that my domain then is all numbers. Okay, sorry class, again, Microsoft Word's hating me today. So the domain is just going to be all numbers except negative 3 and 3. And so the way we write that, remember, with interval notation is negative 3 to, negative infinity to negative 3, union the stuff in between, union 3 to infinity. Okay. And now the difference is that we're going to have a vertical asymptote wherever we have domain issues, except this one actually canceled out. So if you take a look at the original graph, original function, see, these kind of cancel out. And so this one's what we call a removable hole, or a spot where we're not going to have a vertical asymptote at both places. It turns out we only have a vertical asymptote at x equals 3, and that's because the graph looks like this. And so we have this vertical asymptote at x equals 3 only at x equals 3, not at the x equals negative 3. And that's because actually at negative 3 we have an open hole right here. So we have an open dot. Hole. And we call that a removable discontinuity. And that happens anytime from algebra where they cancel out. So where they don't cancel out, like here on the x equals 3, is a vertical asymptote. When they don't cancel out, we're for sure going to get a vertical asymptote. Okay, so I want you to take a look at this one. I want you to pause the video, try it on your own, and then come back, and then I'll have the work out as well. So go ahead and pause the video now. Okay, class, I'm back. So I did sort of like I did above. I did the algebra first, and so this tells me right here that this is not removable. It's still there, and so that tells me that x equals negative 2 is the vertical asymptote. I also did here where I just set the denominator equal to 0. I found both zeros. So the domain is going to be, the restrictions are going to be here and here. Because negative 2, x equals negative 2 is a vertical asymptote, but the other one, the x equals 2, is removable. So that's why x equals 2 is removable. And just to get practice with domain again, it would just be, okay, all numbers except these two numbers, negative 2 and 2, just to give you more practice. I didn't ask you to do this, but just to give you more practice. The domain then would be negative infinity to negative 2, union, negative 2 to 2, union 2 to infinity. Okay. Alright, so the last page we're on is a quick and dirty way to tell what a rational function what type of asymptotes it will have. Okay, and so this last little section is I just want to break down a quick and easy way to tell how to identify the end behaviors of rational functions. Because if we look at any old random rational functions like here or here or here, it can be kind of difficult to tell, okay, what happens as I go, and remember what end behavior means. It means what happens as x goes to infinity, what does the graph do? A big question mark there. And the same thing, as x goes to negative infinity, what does the graph do? And it's really quick and easy way to tell is all you have to look at is the biggest power on top and the biggest power on the bottom. So let's take a look at these examples here. If we take a look right here at this example, all I care about is just looking at these two. The other two do not matter at all, because remember, I'm talking about as x goes to infinity. So as x goes to infinity, I care about the cubed and the cubed on the top and the bottom. I don't care about the negative 10x and the plus 5x squared, because the cube is way more important. So we really just care about the leading terms. And so because these are even, so I say, okay, these are the same powers. So this is basically the same thing as 6x cubed over 2x cubed, and that just cancels out, and that becomes 6 over 2, which is 3. And so what that means is that as x goes to infinity, the graph just goes to that value. And as x goes to negative infinity, f also goes to 3. Okay? And that example of where the powers were the same and the end behavior was just that number is sort of like right here. So this is like example 1. So this is like a okay, where the graph just goes to 3. And in the box there, I'll say that's when they're equal. Okay, it's just going to be just the ratio of the coefficients. Okay. Now what happens when I'm going to skip B for just a second. Let's talk about C. What happens when the power on the bottom is bigger? So let's take a look at this one. Let me erase all this. Again, all I care about is just look at that. And so that is like x squared over x cubed, which is just 1 over x. Okay? And so all I care about then is that if I'm taking as x goes to infinity, what happens to this graph? Well, let x get really big. If I do 1 divided by, some big number, okay, that's 0.01, and if I do 1 divided by it's 0.001. Okay, so as x gets bigger, 1 divided by a big number just goes to 0. And so we get 0. And the same thing with the negative, okay? This also goes to 0. You might think, well, maybe it goes to negative 0, but remember, negative 0 is still 0. Excuse me. And I'm back. My cough is kicking up, so I'm going to have to rush through this, but that is what happens when the power on the bottom is bigger. So that when the power on top is less than the degree in the bottom, we have a horizontal asymptote at y equals 0. Okay, and that would be this example. So this is like in C. I'm sorry, I wish I had these lined up correctly. It's probably not helpful at all. Excuse me. Okay. Excuse me. Okay, and the last little bit is what happens when their power is off by just 1. So if we take a look at this. Okay, the problem with that is that when they're only different by only 1 power, x squared and x is only off by 1. So x squared divided by x Okay. So whenever you get that and you get x left over, then the difference was only 1 power. This is a power 2, this is a power 1. So then what we do actually is we we're going to have a slant asymptote. And the way we're going to find that slant asymptote is we're going to do synthetic division. A slant asymptote looks like this, where we have a graph. The graph ends up shooting off like this, and we have this little really cool slant asymptote where the graph is never going to cross that slant line. And the way you find the slant asymptote is that you just so +1, find a slant asymptote. And so all we have to do is just do synthetic division, which I'll do right here. Let me erase all this stuff. And that's how you find that last little piece. So if I take this, and again, what I want to do is just find the slant asymptote. Okay, so I'm just going to take this and do synthetic division. X minus 4, 1. Not x, sorry. Just 1. Bring the 1 down, and then go from there. Add these. And you get -2. You add that. Excuse me. And then you get -2. And then you get +4. And you get +5. Okay? When I do the slant asymptote, I only care about this. And so the slant asymptote is just going to be y is equal to x minus 2. And so what that means is that the graph has this asymptote where -2, like this, draw in red. Try to make it dashed. Oh, we can't do that. Well, try again. And what that means is that the graph has this asymptote where it's not going to be able to reach it. And it looks like that going down here. Okay. And it has this vertical asymptote right here, like that. Okay. So basically, if you have the power is different by 1, just do synthetic division to get your slant asymptote. And you don't need to care about the remainder at all. So you can, when you're finding the slant asymptote, you can just disregard the remainder. Okay? And all you need is this, is the actual part from the synthetic division that wasn't the remainder. Okay, so that's it for this section. Thanks. My voice is going, but I'll post this on Canvas, and I'll see you next time.